Welcome back. Now, we're going to continue our momentum with replicating different equations from the paper. And we're up to the multi-layer perceptron block. Multi-layer perceptron, or MLP block. I'll call that MLP block for short. And so if we jump into the paper, this is the MLP block. So we've already done this. You might have given this one a shot here. It's very similar to this attention block or multi-head or MSA block, except instead of using multi-head attention, we use an MLP block or MLP layer. So let's jump into the keynote and get a little bit of an overview. Oh yeah, and here's a summary of what we've just done. We're turning figures or images, math, and text into reusable PyTorch code. So there's our layer norm layer, and then we create our multi-head attention layer, and then within this is the MSA block. We've already covered that. So now we're up to equation 3, the MLP block. So what do we want to do here? Well, we've got MLP, multi-layer perceptron, MLP block, and then if we draw some colorful lines, the transformer encoder consists of alternating layers of multi-head self-attention, MSA. We've already done that. Look at us go. And MLP blocks, equation 2 and 3. So alternating MSA and MLP blocks within the transformer encoder. Layer norm, we've seen layer norm, is applied before every block. So just like here. And residual connections are after every block. So much like our MSA block has a residual connection, we haven't coded that just yet. The same thing is with our MLP block. And recall the residual connection is equivalent to adding the inputs to the outputs of a block. And that enables larger and deeper models because it prevents our gradients and weight updates from getting too small. So let's start to replicate this in code. Or what we might do actually is just explore the paper to find out what the MLP block is created. We know what layer norm is. Let's find out what the MLP block. So if we jump into 3.1, which describes an overview of the model, we've read here, equation 2 and 3, then there's one single line that describes the MLP. The MLP contains 2 layers with a GELU nonlinearity. So let's see what this looks like in pseudocode. We go here, I'll bold this, MLP is equal to, this is from section 3.1. So previously we may have defined an MLP. MLP is quite broad. It equals a quite broad term for a layer or series of layers, or a block really, maybe a block, for a block with a series of layers. So layers can be multiple or even only one hidden layer. So we see here that the VIT paper has an MLP with 2 layers. So it's giving us that. And by layers, usually they mean fully connected. I'm just going to write this down because there's multiple different terms. Layers can mean fully connected, dense, linear, feed forward. All are often similar names for the same thing. In PyTorch, they're often called, this is torch nn.linear. So PyTorch calls them linear layers. And just for reference, in TensorFlow, which is another very popular deep learning framework, they might be called, I think it's tf.keras.layers, or maybe tf.keras.dense. So TensorFlow, dense. TF-keras layers dense. So that's different names for the same thing. So what is a GELU nonlinearity? Let's look that up. What is GELU nonlinearity? There we go, GELU explained. Okay, so the Gaussian error linear unit, or GELU, which is similar to ReLU, which we've used before, is an activation function. The GELU activation function is, I'm not actually sure where that is the standard Gaussian cumulative distribution function. The GELU nonlinearity weights inputs by their percentile rather than gates inputs by their sign, as in ReLUs. Consequently, the GELU can be thought of as a smoother ReLU. Okay, here we go. So the ReLU is this hard orange line, which we've seen before. So let's go ReLU nonlinear. What does that look like? So ReLU is this, it zeroes all the negative inputs. Then what happens with GELU is we give a little bit more space for some negative inputs to come in. It's a bit more smooth there. And then of course we've got LU as well, which is different again. So this is the thing with a lot of activation functions. If we go into PyTorch activation functions, of course they implement different methods of how they work, but they all kind of do a similar overall process, is that they add in non-linearities. So instead of just being purely straight lines, we get some sort of non-linear line. And remember, machine learning, what can you draw with an infinite combination of straight and non-straight lines? Well, you can draw some pretty intricate patterns, can't you? So here we go. We can implement GELU with that. So let's bring this in. If in doubt, code it out. So GELU in PyTorch. There we go. And if we read the docs of what that does, applies the Gaussian area linear units function. Wonderful. So we've got the GELU function there. We've got this little gap here for values that are negative. So we'll see how we can implement this in code. And in fact, we've already got the pieces of the puzzle here. How about we create it in pseudocode? So the pseudocode for this is going to be, this is where your challenge is going to come in. You'll notice I'm going to start issuing more and more challenges because I think our skills are getting pretty good, you know? So x equals, this is going to be the input to our MLP. So let's call this MLP, is going to be 2 layers with a GELU nonlinearity. So we want x to go through linear, and then we want it to go through nonlinear, and then there's one piece of the puzzle we actually haven't coded here yet, drop out, linear, and then finally nonlinear. And then maybe drop out. Or actually, we'll have a look at the paper and see what they did. I think that'll be it. So linear contains 2 layers with a GELU nonlinearity. So we've got our linear, nonlinear, dropout, linear, dropout. So I think that'll be the order, but dropout, we need to talk about this. Dropout, another one of those treasures. We're explaining a nonlinear paper in a very linear way. So dropout, let's go here. Dropout, when used, we've touched on this before, is applied after every dense layer. And what did we say before? A dense layer is another word for a linear layer. So in PyTorch, we call them linear. In TensorFlow, you might call them dense or a fully connected layer. So we need dropout after our linear layers in our MLP. So give that a shot. I'm just going to copy this in here actually. There we go. Dropout. That's one of those treasures you kind of have to search for in the paper. So if we create a class here, we're going to call it MLP block, inherit from nn.module, and implement the MLP, implement dropout, and then of course in the forward method, you'll want to pass it through. If we go back to figure 1, you'll want to pass it through a norm and then through the MLP block and then return the output so we can create the residual connection later. So give that a go and we'll do it together in the next video.